Nicola to explain a little bit about the hot wire technique.
Sorry.
No problem.
Sorry.
No problem. He's the bad guy. So you need an hot wire when you want to measure velocities. So, and in particular, you need an hot wire when you want to measure turbulence. And the reason why is because even if the hot wire has a drawback that it is an intrusive measurement technique, and it's point-wise, and kind of depend also on the temperature, but all these are drawbacks that are less important with respect to the major advantage of the hot wire technique, which is the fact that it's very fast. So if you want to measure turbulence fluctuations or anyway to characterize the flow from a statistical point of view, you might need a hot wire. So how does it work? You have a wire, which is over here. Basically, this is the instrument. I think it's more or less 8 micron diameter, and the material is usually tungsten. So you have a current, electrical current that flows inside the wire, and due to Joule effect, it heats up. So what happens is that an energy balance is established between the wire itself and the environments, and the flow. So as the flow changes its characteristics, also this energy balance changes. So, and this is what you actually can appreciate through the hot wire. So there are two operating modes. One is the constant current operating mode, which has bad frequency response characteristics. So nowadays it's not used anymore. And the reason why it has low bad characteristic from the point of view of the time response is that his time response is related to the inertia, to the thermal inertia of the wire. And then there is the other operating mode, which is the constant temperature operating mode, which is on the other side is very fast, with a maximum frequency that goes above the 30 kilohertz. And the reason why it's so fast is because in this case the inertia of the system is the electrical inertia, due to the fact that you have a Wheatstone bridge and you have a closed loop, and this inertia is usually very small. So in this way your hot wire, your system, your anemometer is able to be very, very fast. So the hot wire is just like this small wire. So in the Wheatstone bridge is one of the 4 bridges, but the full hot wire in terms of anemometer is the full circuit. So if you want to characterize the properties of your hot wire, you are not characterizing only the property of this part, but of the entire system. So in the real setup, we have here the hot wire. We have the wire that is linked to the actually detector, and you have the full box, which included the Wheatstone bridge, the amplifier, and the feedback loop. So the first thing that you do when you get to the lab and you work with hot wire is the dynamical calibration. Why you want to calibrate dynamically your instrument? For 2 main reasons. First of all, you need to know if what you want to see can be appreciated with the instrument that you are using. So let's say that you want to measure a very fast phenomenon, and then you realize that your instrument is not adapted for that. Then either you change the instrument, either you have to change the technique. So the first important thing is to characterize how fast I can detect like the change in my flow. The second reason is that when you have to acquire data, you usually digitalize them. So what we'll have in a real setup is that instead of an oscilloscope like this one, you will have a filter, and then the output of the filter goes to a computer with a card which digitalize your data. And for this procedure, it's extremely important to know which is your maximum frequency, because otherwise you would encounter aliasing. And you don't want to have aliasing because it's impossible to remove this spurious frequency a posteriori. So if you get, then basically you have to stay with it and you don't even realize. So it's very important to have a dynamic calibration even before starting to do the static calibration. So now Nicolas can explain a little bit.
I will show you how we do the dynamic calibration. So first of all, as you said, inside of the anemometer, what you have is a Weston bridge and a feedback loop. The thing is that before to start the feedback loop and be able to acquire, you get to ensure that you are more or less equilibrated for the Weston bridge. Why? If you are not equilibrated and that you launch the feedback loop, it will just don't understand what's happening, send too much current, and you will burn instantaneously your wire. The first point for the ones who will do the lab is that, okay, one more point. So inside of the Weston bridge, you have, like you said, like Federico said, one of the resistances that is the hot wire, and two resistances that are fixed, and one resistance that you can set up. In that resistance, you get a resistance, a capacitance, and a coil. So first thing, I set my my resistance in order to be more or less equilibrated for the Weston bridge. So here, I got to look here. Okay, no. Okay, so here I'm more or less equilibrated. I can start the feedback loop. So now the feedback loop is engaged and the hot wire is measuring. Now what you want to do is to observe the response of the hot wire for a peak of Dirac of wind, ideally. Now to create a wind that looks like a Dirac peak, it's very difficult, so you got to have just a zero wind after to come back to zero. It's more or less impossible. So what do we do is that we will simulate electronically the excitation of the wind. So you have this button here, okay, square wave generator, so you simulate the square wave of wind with an electrical signal, and what we see here is the response of your hot wire. So now I can start to set up my hot wire in order to obtain a good response. What do I mean by a good response is that, so the resistance, you don't change it anymore, or you burn your hot wire, and then you get a capacitance and a coil. The capacitance will change the damping of the electronical system. So of course, if I put too much damping, I just erase my response. So you got to put not too much damping. But if I don't put enough damping in my electronical system, what will happen is that, okay, so you got a response for one change in the wind, so one side of the square signal. And if I put less and less and less, what you see is that, okay, you got a first peak, a second peak, a third peak, and if I put even less damping, what's happening is that the system will never stop to oscillate, and so you are completely losing all your time resolution. Okay, it's oscillating for infinite time, so it's finished. So the game is to try to obtain a response more or less like that. A response more or less like that for the system, for the electrical system that you have. Normally, when you see the response and then a little overshoot, it means that you are close to the critical damping, and so normally, mathematically, you are more or less at the best compromise between damping and not damping, so you don't erase too much your response and you have a good time resolution. So what I will try to do, so normally, yes, okay, so here, okay, yes, I have already a good answer. And if I change the coil, so I show you the damping, and if I change the coil has not so much effect on the response. You see the effect of, if you want to see the effect of the coil, so okay, I'm narrowing a little bit my response, but that's okay. So here I'm losing a little bit of time resolution. If I put the coil at the maximum, normally I have a little bit better time resolution. So now, thanks to that, I will be able to determine what is the maximum frequency of what I can record. So in order to do this, what you will do is that you will take, so you get response, you take the maximum of the response, you take 1/3, and this is a characteristic time of the electronic system. With this characteristic system, you have a more empirical formula that gives you, this is the maximum frequency. When you determine, so in order for the ones that will do the love, what do you do with the oscilloscope? You send the square wave, then you try to obtain 3 squares of intensity, so you can change the amplitude of the square wave. Okay, I have 3. Now I took like that. I take 1/3, and you have an estimation of your typical time, and you can determine what is the maximum frequency. Then, when you have this maximum frequency of what you can record, you divide it by 2. Multiply, in order to for the Nyquist or.
Yeah, you
multiply by 2, and you remove everything that is more than 2 times this frequency. So you can set up your filter. Yes. Now, one thing here, I did it, but it's not the good. I did the calibration, but it's not the best way to do the calibration. Why? Because I'm far from the conditions that I will try to record. So now, if you observe the response of the system with some wind, what you see is that, okay, you have a first oscillation, a second oscillation, a third oscillation, a fourth oscillation. So when you try to set up your technical system, in fact what's happening is that when you start the wind, you are changing the temperature of your, the conditions of working of your hot wire, you change the resistance and change the resistance of your hot wire, and finally you are not exactly in the same condition. So you have changed your mechanical system. So now you got to do the setup. Now usually what you do for hot wire measurements is that you do the setup of the mechanical system at the maximum velocity that you should observe. So here normally what you do is that you put your hot wire in the center of the jet. So normally now, yes, we have done the dynamic calibration, so we can set up our filter. Now the second thing to do is to do the static calibration. I'll let you continue.
So is it clear so far, more or less? So just a little one more comment about the signal conditioning. So we have talked about how important it is to know the maximum frequency of the instrument. In this way you can establish a cutoff frequency that becomes your maximum frequency that you can appreciate. In this way you are sure that if you put the sampling frequency twice as the cutoff frequency, you don't find any highlight in your data. The other important thing is the amplification of the signal, because as you know, your board has some characteristics in terms of when discretized, yes, it has some limits. So if you don't amplify properly your analog signal, what you will end up is with a digital signal that will have lost all the possible resolution that is guaranteed by the digital board. So it's not only important to set a frequency, cutoff frequency, but it's also very important to establish a good amplification of the signal in such a way that you exploit the full range of your board, of your card data on your computer. So once you have more or less characterized the dynamical behavior of your system, now it's time to have a calibration curve. So we have said that what you actually measure with the hot wire is a change in the voltage. So it's an electric expansion that you are measuring. So what you want to do is to build such a curve. So you want a curve that can relate the anemometer voltage with the velocity. How you build such a curve? First of all, you have to take many points close to the zero, because here is the most sensitive part. Once, if you don't have enough points here in this part of the curve, what you will have is that you will have a fitting that will lie. So you will not have a fitting that will be accurate in the whole range of velocity. The second thing is that the zero velocity has to be acquired when you have the cap. So it's important that the zero velocity is acquired with a cap. The reason why is because, of course, this is a very sensitive instrument. So as soon as you have an open environment, you will always have fluctuations and changes in temperature. So the 0 point you want to take it with the cap on.
Normally, yes, you see difference. It's not so much, but if you are wrong in your zero, when you will measure a real zero, so that is inferior, you will have the feeling. When you see your curve, you will have the feeling that you are measuring a negative velocity or something like that. This is of course completely false. But so it's important to have, and especially because the last points of the curve are the most critical for the reconstruction of the curve. The points that are close to the zero will have a big effect if they are not well done. You will have a curve that goes down and then go back or things like that. So it's important to have good zero and the points after that should be really good.
So the last trick is that, of course, when you will measure zero velocity, so you don't have any velocity, and you know that you don't have any velocity. But of course, due to fluctuations of the air in the environment, and you will always get like a certain amount of a small velocity, like a small voltage. So the important thing is that you will never get like such a curve that exactly intersecate at zero. So you will always get a curve that is always a little bit drift. The point there is that you know that is your zero condition, so you have to translate your curve in such a way that becomes the zero of your system. How you do this calibration? Because of course here you imply that that you can build like a relationship between the voltage and the velocity. But so you have to build the velocity. So you have to know which velocity you are using. So in practice, when I open this handle and I have a certain jet getting out of it or of the nozzle, you want to know exactly which is the velocity that is getting out. Otherwise, when you will put your anemometer, you will not have any way able to build such a curve. How we do it? Usually you have such a nozzle that is very well characterized. That is a nozzle that is done for calibration. For the people that will do the lab, they will use directly this nozzle. And what do you do? Basically, you have a barometer through which you measure the pressure in this point, and of course you know the pressure at the exit, which is the atmospheric pressure. So if you assume that the velocity here is more or less zero, due to the fact that inside the nozzle the velocity is highly accelerated, what you will do is by applying the Bernoulli equation, you will be able to retrieve through a pressure measurement your velocity at the nozzle. So in this way, you are able to characterize the velocity of the jet and then build such a curve. So the last hint that I can give on the calibration curve is that as soon as you build this curve, don't switch off the instrument. As soon as you switch off the instrument, you lose your calibration curve. And the reason why is because, as Nicolas was showing, you have to balance the system. The anemometer is not only the hot wire, but it's a complex system. There is an electrical circuit, so as soon as you switch off it, you turn it on again, your calibration could have been lost. So you do the calibration and then you do immediately the measurement. Otherwise, if you go home to have dinner or to sleep, don't switch off the instrument simply, because otherwise you have to do everything again. Or in case for people that don't do calibration again, will find crazy results when it's about interpreting them. So for what concerns the instrument itself, what we had to say is more or less there. Do you have any question before we move to the demonstration? Everything is more or less clear? Okay.
So now what we'll do is that we'll see a little bit what we can observe with by exploring the jet with the wire. One other thing about the static calibration. When you do static calibration with the nozzle, you got to be in this region of the nozzle, so just in front of the nozzle. In this region of the jet, just in front of the nozzle. Why? Because in this region is the potential core. The potential core has the characteristics that first, the velocity inside is very close to the constant. So as you can see, so here what we have is a mean velocity profile. So we take the hot wire and travel like that. We record the signal and we take the mean velocity. And what you see is that outside of the jet there is zero. And while you are in the jet, you have something very flat, you have very constant velocity. So it's good for the calibration, of course. And moreover, if you are still in this region, what you have, and close to the nozzle, what you have is that, as you can see here, so the black curve here, is the turbulence intensity, so you have a very small turbulence. What means that, in fact, your velocity is very constant and very well defined. So now, start this, and you will see what are the different regions to get here. So, as I said, you got the potential core with a very constant velocity. You got the outside of the jet with zero velocity and more or less zero turbulence. And then you have, between both of them, you have the mixing layer, which will contain all the turbulence. In terms of velocity distribution, what you will observe, so if you are here at the black point outside of the jet, you have a velocity which is close to zero, and with not so much turbulence. The turbulence is related to the standard deviation of the distribution, and so that's why you have very well defined close to zero velocity, very small because no turbulence. If you go at the green point, so inside the potential core, what you see is that the velocity is different, but we have more or less we have a very weak turbulence, and so you have also a very well defined something that starts to look like a tube. In the opposite case, if you are in the middle of the barrier or the mixing layer, what will happen is that your mean velocity will be something like the half of the jet velocity, but you have much turbulence, and so that's why the standard deviation of the distribution is bigger than the distribution of the outside and the potential region. So we can see it easily. So here normally here I'm in the potential core, and you will see that okay. So here, yes, you see clearly turbulence, you are at the mixing layer, and now I reach again the outside of the jet. So now, statistically, a few things a little bit more interesting. So we have put a little bit. Now, what will happen when you are at the orange point? At the orange point, you are just at the limit of the potential core. So what we will observe is a velocity that is more or less close of the one of the potential core. Okay, so you see that 95% of the signal will be close to the one of the velocity recorded in the potential core. But when you are here, sometimes you have the mixing layer that is a mean velocity that is the half, and so you can have a vortex that escapes from the mixing layer and will come and touch the hot wire. And so what you will see is that normally you are more or less always in this region in terms of velocity, but sometimes you will see a peak, a negative peak, and a decrease in the velocity. So it's easy to find the limits of the potential corridor. So we go in. Okay, and when you see. Okay, so you see, no, most of the time you are in this region, the signal is always the same, and sometimes, just sometimes you see one negative peak, because the vortex is just passing through the hot wire, and so you see clearly one of the vortex that is passing through. Then you got the opposite between the external part of the jet and the mixing layer, so here, the white point is the white curve, and so here is the opposite. Most of the time, what you will see, yes, there is a white curve. I come to detail. So you will see more or less a velocity of zero, but sometimes you will have a vortex that will escape from the mixing layer and add some velocity to the flow. So normally, what you will observe what's he doing? Yeah, okay. It's a little bit less well, you can see it a little bit less well than the case before, but what you can see is that your signal is most of the time here. You never see a negative peak because it's not possible. That's okay, yeah. You can never see a negative peak because normally you have a velocity of zero and you cannot have something that is less than zero. It's the absolute velocity, so you don't have negative velocity, it's impossible. And so, most of the time you are here, in this window, and sometimes you see one positive peak. Every positive peak is a vortex that escapes from the mixing layer and that reaches the fire. Okay? So, normally we have more or less finished the target, finished the presentation. So, you are welcome for questions and